All right, we're back. Chapter 17, Part 2. Now we're going to talk about glaciers. So I'd said to you that we know that most of the northern hemisphere was covered with glaciers during the last ice age. In fact, Chicago was under about 2 miles of ice at one point. So how do we know this? One of the markers of glacial actions left behind is glacial drift, and this is the movement of sediments by glaciers. Glaciers can act like big, huge bulldozers of ice, and as they expand, they can push and move dirt and ice and rock. And when they melt, they leave it behind, and that's called glacial drift. And it has a different type of pattern than stuff that is moved by wind or water or rain. So we can look at that. An interesting example right here are what they call glacial erratics. So oftentimes we find these erratics. They're called that because you'll find them in the middle of a field, and the field has no rocks in it, but there's a big, huge boulder in the middle of it. And when you analyze the rock, there is no rock nearby that is the same type. In fact, the parent of this rock may be 300 to 400 miles further away. So how did it get here? What happens is basically as the glacier was moving south, this piece of rock was picked up by the ice and dragged along with it, 200, 300, 400 miles south. When the ice melted, it was just left there. So glaciers leave behind a lot of different materials. And a lot of times there's water involved with this, so they call that drift. So anyway, what is a glacier? And a glacier is nothing more than ice. It is a very, very big piece of ice. Now, it isn't like there was a very cold winter, it had an ice storm, and there was a big ice cube left behind. It actually forms from years and years of snow. And in an environment where the snow never melts, every time it snows, you add more snow on top. So imagine in Chicago, right? And we have our first snow in November. And it may melt, we have the second snow, and finally by December or January, we've got snow in the ground, maybe till March, and it melts. But what would happen if that snow in March never melted? And maybe it didn't get any more snow all summer, but it didn't melt. But then next November, it snowed again. You would add more snow. And over years of doing this, you'd have thicker and thicker snow. And so what happens is glaciers form this way. The snow adds up, it accumulates, gets thicker and thicker and thicker, and it has a lot of weight. And eventually, the weight of the snow is so great that it squeezes out any kind of air in the snow at the bottom, and it becomes ice. Okay? So glaciers have to form in an environment where it is cold and cold year round. So if it ever goes above warming more than a day or two, enough to melt the snow, glaciers will never form. So here's an example. You have some snow, it falls on the surface. And the top of the snow is the newest snow, it's the freshest snow. It's almost 90% air, nice and fluffy, pretty snow. But as more and more snow is added over time, the weight of the snow above it begins to smush it and crush it. And it goes from 90 to 50 down here at the bottom. At the bottom of the glacier, it can be as little as less than 20% air and almost all solid ice at that point. I like this picture. It kind of shows you that. This is the edge of a glacier here in the water. And you can see that as it goes down from the top, it becomes much more compacted looking. You can also see these unique bands. That's because, think about this, when the snow falls, what if a volcano erupted nearby that year and that dust is in the air, that ash? That might make the snow a little bit different color. So we can actually use glaciers, and we'll talk about this in a few more slides, to actually measure and date certain atmospheric events. Now I said that glaciers move. How does ice move? There's two ways. Either one, it actually will kind of ooze, almost like caramel or cake batter, and that's called plasticity. So over time, right, the glacier forms up here high in the mountain, and there's just so much of it, and it just actually basically oozes down the side of the hill. The other thing, it actually will flow over the surface as well, sliding slowly. Now, glaciers move, but it is very, very slow. Every glacier is different, but you can say at the most average about a centimeter or two a day. Not always in the same rate. Maybe it flows faster in the summer when there's more melt, maybe slower in the winter. And what affects that? Air temperature, if it warms up, um, if it's going down a really steep mountain versus a kind of a slower one. And then the amount of water, we'll talk about that. It's called vasolubrication at the base. But oftentimes glaciers will move not steadily, but they'll kind of go faster, slower, faster, slower. And a glacial surge is when it just speeds up for a few days at a time. So here's kind of an example of a glacier moving down the side of a mountain. It's in this valley right here. Now the glacier will move fastest in the middle and slowest at the edge. And that may seem kind of weird that it may move, but I just think about if you've ever poured brownie batter into a pan or cake batter, right? And as it kind of spreads out, the middle part is the most liquidest, if you will. And that's the same thing here. Now, scientists, when they study glaciers, they have to account for the mass balance. And this just basically is a way of looking at the size of a glacier and if it's growing or shrinking. So, inputs to a glacier. Glacial mass balance is the difference between those inputs to a glacier that increase it and the differences between those that decrease it. So what would be the inputs? Well, like we said, snow. Every year it snows. So snow, the adding of more snow creates more glacier. And what would be something that decreases the volume? Melt. The glacier at the bottom melts, or parts of it break off into icebergs. And so you basically take those two, and if there's more glacier being made than being lost, it has a positive balance. It's growing. And if there's more glacier being lost than being formed, it has a negative balance. The zone of accumulation is the part of the glacier where it's growing. So if you think about a glacier up in the mountains, I'll show you how this looks. The part where it grows is the zone of accumulation, whereas the part where it is not growing or shrinking is the zone of ablation. So accumulation, ice gain exceeds loss, and the zone of ablation, ice loss exceeds ice accumulation. I love the fact that the end of a glacier is called the toe. I'm going to show you a picture in a little bit. But in between these two, in between the accumulation and the ablation, you have what's called the equilibrium line. So let's kind of show you what it looks like. Here's a glacier up in the mountains. Okay, so up here high in the mountains, it snows every year. The snow doesn't melt, it adds up. So the glacier is growing. It's gaining more snow every year. So this is the zone of accumulation. Now it loses some because the glacier flows downhill. So it adds new ice every year, but some ice goes downhill. But it's adding more ice than is leaving. As it goes down the mountain, now we get here where it gets warm enough in the summer for the ice to melt. So now the ice is melting a little bit down here. And there is more ice melting than ice coming to replace it. So it eventually ends right here at the toe. So this is the zone of ablation down here. This is the zone of accumulation right here. And this is that transition line between the two, the equilibrium line. So using this idea of the glaciers growing or shrinking, right? A glacial advance would look like the toe is coming at you. If you were standing in front of it, it's moving down slope. And that means the glacier is growing. Conversely, if the toe of the glacier is going back up towards the source, then it's shrinking. So let's go back to that slide. If you were to come here once a month for 10 years and take a picture, and the ice is going this way, back up, it's shrinking. The ice looks to be retreating. But if it's coming this way at you, and every year it's a little further out, then it would be advancing. And basically, if a glacier is advancing, then it's gaining size. And if it's shrinking, then it is retreating. So, now, by the way, if you were to actually measure the front of the glacier continuously, it goes back and forth every day a little bit. But we're looking at the general overall patterns. So here's a stationary glacier. If you were to stick a marker right here at the end of the glacier at the toe, the glacier would always stay here. It's flowing downhill, that's no problem. But what happens is, it's growing here, the zone of accumulation, at the same rate it's shrinking in the zone of ablation. So as fast as the snow is made, it's lost. And so what happens is the overall effect is the glacier stays the same size. Okay, but what happens if it's making more snow than it's losing? Then the glacier is going to be looked to be advanced. So let's imagine that it's up in the mountains, and every year it's a little bit colder. So what happens is it stays frozen, or more snow stays frozen, a little bit lower down the mountain, which gives it more area, which means there's more glacier being built. But what happens if climate warms? Well, then, if it's warmer every year, the area where it stays cold in the mountains is smaller. So now there's a smaller zone of accumulation, less snow. And what happens is, even though the glacier is still making snow moving down the mountain, it's melting faster than can be replaced. So it looks to you that the glacier is going back uphill over time. Now, the reason I mention that is when we look at most glaciers around the world, they are in retreat. And this is usually given as one of the signs of global warming because we have noticed this trend for about the last roughly 100 years. There are one or two exceptions, but that's one out of like 300. Most glaciers are melting faster than they can be made. And scientists monitor this because it's a really good way to, examine and quantify climate change. So how do we monitor that? Well, you can take pictures. Right here is a picture of the same glacier every year for so many years. Scientists go out, they monitor it, they take time-lapse photography, they'll take measurements of the ice, how thick it is, how much water versus air content is it. They'll use lasers to mark if it's moved how far. And all in all, when we do that, this area here in Alaska, here's a glacier in 1986, the Columbia Glacier. This is where it ended, and this is where it ends today. So it's moved about 10 miles up its valley. And we're looking at 3 other glaciers in the area. We look at their mass balance, their overall size, and you can see all 3 have shrunk. And again, this is something that we see around the world. So now that you know what glaciers are, I'm going to stop right here and come back, and we're going to talk about the different types of glaciers in part 3.